Hello and welcome. Today we're going to start with section 6.1 on angles and their measure. So just a quick little bit of vocab to get out of the way. So we start with vertex V, and we send a ray off from that vertex. If we're looking to make an angle, I can start with a vertex, make one ray, and call that the initial side. And another ray coming off of it, that will be our terminal side. If we're rotating this way, it's a positive angle. Of course, the other way then, clockwise, would be a negative angle. The sort of standard position that we'll use vertex is at the origin O, 0, 0. And initial side is the positive x-axis. So it's going to be sort of just our default settings when we're making angles. Degrees, there's 360 degrees in one full revolution. So basically start at the initial side, spin all the way around until you're back where you started. So a quarter of that would make a nice, neat, pretty right angle. A 90-degree angle is a right angle. Of course, doubling a right angle, we're at then a straight angle. It should be 180 degrees. So next we'll sketch a few angles. We'll start with 60 degrees, and I'm just going to sort of rough these in for the moment. So picture yourself in an XY plane here. So 90 degrees is up here, 45 would be the middle, so 60 degrees would be more along the lines here. So initial side, terminal side, and here's our 60 degrees. If they ask for, say, a negative 45-degree angle, so our initial side here, negative is telling me rotate this way instead of this way. It's rotating clockwise instead of counterclockwise. So 90 would be the full right angle, half of that is 45. So this is our negative 45-degree angle. So next we'll take a look at a 270-degree angle. So here's the 90, 180, 270. So if this is our initial side, this would be our terminal side, but instead of this is our angle. And sometimes they have us go around more than once. 420 degrees We'll spin once around is 360, so we'll take the 360 off of that. So spin once all the way around and go 60 more degrees. There's our 420 degree angle. Now we can also break up degrees into both minutes and seconds. 1 degree is 60 minutes. This prime symbol here is minutes. And 1 minute is 60 seconds, double prime being seconds. And so we kind of have to be able to switch back and forth between degrees, minutes, seconds, and decimal degrees. So we'll start with 40 degrees, 25 minutes, 36 seconds, and we'll turn that into decimal degrees. So we want all of these in degrees. So 40 is already in degrees. 25 minutes. If 1 degree is 60 minutes, 1 minute is 1/60th of a degree. And 36 seconds. First we convert to minutes, then turn the minutes into degrees. So we have 40 plus 0.41, and the 6 goes on forever, 0.01. So this would be 54, or my apologies, I'm looking at the next problem. 40.426, 6 repeating degrees. So this would be our decimal degrees. So again, just turn those minutes back into degrees, turn the seconds into minutes, and the minutes back into degrees. Alright, so again, we'll also have to go the other way, decimal degrees into degrees, minutes, seconds. Doesn't always work precisely. Sometimes we'll have to do a little approximation, like on this next one, 54.2835 degrees. So we'll keep the 54 degrees, and then we have 0.2835 times 1 degree. So this is also in terms of degrees. But remember, 1 degree is the same as 60 minutes. So hang on to this 54 degrees. 0.2835 times 60 minutes. So now we have 54 degrees plus 17.01 minutes. So that's just doing the product of those two. We'll hang on to the minutes and turn the 0.01 minute into a number of seconds. So hang on to the 54 degrees, hang on to the 17 minutes, and 0.01 times 1 minute. 1 minute is 60 seconds. So 54 degrees, 17 minutes, 0.6 seconds. They might have us leave it there. If they ask for nearest degree, we can round that then to 1 degree. Or not nearest degree, my apologies, nearest second. So if they want the actual, leave it there. If they want an approximation, they want the nearest second, 54 degrees, 17 minutes, 1 second. So we will be sort of switching back and forth between degrees, minutes, seconds, and decimal degrees. Alright, so next we get to play with the arc length of a circle based on an angle. And you'll see pretty quickly why I am not an art teacher. But my drawings have kind of the necessary information in them anyway. So S here is the arc length. I'm looking at how big is this chunk of the circle. So we can consider ratios. You can kind of think in terms of a similar triangle type of situation. So I can sort of add in a second one of these guys. We'll use thread, and we'll call this other angle theta sub 1, and this other arc length S sub 1. And the ratio of the angles is equal to the ratio of the arc length. So in other words, theta to theta 1 is equal to S to S sub 1. And for this one, we're going to let theta 1 equal 1 radian. So 1 radius of the circle. So if that's 1 radius of the circle, S sub 1 is equal to R. So now we have theta to theta 1 is now equal to S to R. And if theta 1 is 1 of these radians, then we can have theta over 1 is S over R. In other words, S equals R theta. So the arc length is R times theta, R times the number of radians. And that should fit with what we know. Let's say for 2 pi radians, then our arc length is R times 2 pi. 2 times the radius is the diameter. Pi times diameter, that's the circumference of the full circle. So the full circle is 2 pi radians. So 1 revolution is 2 pi radians. So pi is half a revolution, in other words, 180 degrees. 2 pi radians is 360 degrees. Now, if we just go with the simpler of those two equivalent statements, 180 degrees is equal to pi radians, that is your sort of Rosetta Stone to convert between the two. So degrees and radians. So for example, 90 degrees. 90 degrees multiplied by 1 pi radians is the same as 180 degrees. The degrees cancel, so it would be pi over 2 radians. Generally, when we're measuring radians, we don't necessarily write the word radians next to it. It's sort of implied that we're talking radians. So generally, we would say 90 degrees is pi over 2 and know that we're talking about radians. So if our radians are 5 pi over 2, again, to find the degree, we would multiply by 1 using our little Rosetta Stone here. So then 5 pi over 2 radians, I want that in degrees. So I want the degrees to stay, I want the radians to cancel. So the pi's drop out. So half of 180 is 90, so 90 by 5, so 450 degrees. That should make sense that that's more than 360 degrees, since 5 halves pi is more than 2 pi, 2 pi being a full revolution of 360 degrees. So try a couple of these on your own. 45 degrees, make sure you can turn that into radians. Make sure you can start with 3 pi over 4 radians and turn that into degrees. Alright, so next we have just a nice little sort of sample problem using this idea of arc length. And that is to do with latitude on the Earth. So here is the center of the Earth, and here is a city. The latitude is the measurement of this angle. E got out of control on me there. So Chicago, 41 degrees, 52 minutes, 55 seconds, rounded, north. And Milwaukee, 43 degrees, 2 minutes, 20 seconds, also north, rounded. For this problem, we're going to look at approximating the distance between the two just based on the difference in the angle between Chicago and Milwaukee. So we're going to assume a negligible difference in longitude. In other words, we're going to ignore drift east or west. We're just going to look at distance in terms of north-south line. So that's one of the simplifying assumptions we'll make for the problem. Also given in this problem, we'll use 3,960 miles as the radius of the Earth. So we find the difference between the two cities. So 43 degrees, 2 minutes, 20 seconds, minus 41 degrees, 52 minutes, 55 seconds. And we do have to do a little regrouping there. So I'll borrow one of these minutes, turn that into 60 more seconds. So now we have 80 seconds minus 55 seconds, so 25 seconds. 1 minute minus 52 minutes. Again, we'll have to do a little bit of regrouping there. We'll borrow one of those degrees, turn that into 60 minutes. 60 minutes plus 1 more minute, 61 minutes. So 61 minutes minus 52 minutes, 9 minutes. And 42 degrees minus 41 degrees, 1 degree, of course. So if we go to decimal degrees for this, so this is in degrees, minutes, seconds. Decimal degrees, hang on to your 1 degree. It's 9 times 1/60th of a degree plus 25 times 1/60th times 1/60th, turning it into minutes and back into degrees. So theta here, a little plug and chug in your handy calculator there, and we got 1.1569, and then a whole bunch of 4s repeating forever. That is our decimal degree. We have it in degrees. We'll turn that into radians. So 180 degrees is the same as pi radians. So theta is approximately 0.02019 radians. And remember, for arc length is r theta. So S equals our radius that was given on the previous page as 3,960 times theta in radians, approximately 0.02019. So approximately 79.96 miles. Depending on if you kept all of the numbers in here and did that times 3,960, you might get either a 6 or a 5 in the hundredths place, but approximately the same distance. Don't forget your units on there when you're answering a word problem. Is a 79 a number of degrees, minutes, seconds, miles, dollars? What are we measuring? So that is our approximate distance from Chicago to Milwaukee. And again, assuming we're talking north-south only, not any east-west drift that we have. So next up, we look at the area of a sector of a circle. So here is our angle theta, and we're looking to fill in that area, and we'll call that A. Again, we'll just make a second one. We'll call that theta sub 1 with area A sub 1. Now we know if suppose theta 1 is equal to 2 pi, then we would have the full circle. And if we have the full circle, we know that the area then is pi r squared. And we use our ratios again. Theta to theta 1 is A to A sub 1, and fill in what we know. So theta to 2 pi is worth A to pi r squared. So then A is theta pi r squared over 2 pi. So the area if we know the angle, would be, notice the pi's drop, theta r squared over 2. So that will be in square units. All right. Our next little topic here, linear speed. So linear speed of an object in circular motion. Picture tying a small stone to a string and spinning the string around in circles. This is talking about how to find the linear speed. Linear speed, also called velocity, distance over time. Well, if we're talking circles and angle theta, arc length s, and radius r, our velocity is arc length divided by time. How much time it takes to get from point A to point B. Now the angular speed, which is a lowercase omega, is theta radians over t units of time. So it's just talking about how many radians per second, year, minute, whatever interval of time that we're measuring. Whereas the linear speed is just talking about a distance traveled instead of a number of rotations. So if we look for relationships between the two, though, arc length, recall, was r theta. So velocity by substitution would be r theta over t. Notice theta over t is also the angular speed. So we can also say that velocity is r omega. Alright, so let's put some of those to work. So let's say we have a radius of 5 feet. And we're going to spin it at 200 revolutions per minute. And we're going to let the object go, and we want to find the linear speed when the object is released. So let's find omega, the angular speed. 200 revolutions per 1 minute. 2 pi radians are in 1 revolution. So then this will give us radians per minute of angular speed. So 400 pi radians per minute. So our velocity we saw was r times omega, so 5 feet times 400 pi radians per minute. So 2,000 pi feet per minute. And then depending on what units they want, these are acceptable units. If they want a more relatable unit, if you maybe want it in miles per hour, let's say, that's pretty easily accomplished then. So 2,000 pi over 1, and that's in feet per minute. One mile, 5,280 feet, and 60 minutes are in 1 hour. Then we get the minutes to drop and the feet to drop an hour in miles per hour. So plugging and chugging, this ends up at about 71.3998 miles per hour. So if you're swinging a little pebble on the end of a 5-foot rope and you're spinning it at 200 revolutions per minute, when you let it go, you're going a little north of 70 miles per hour. All right, so some problems to try out. If you're just doing the book version, 6-1, 3-10, all 11 to 95 odd, 107 and 109 are what I would recommend. If you have any questions, please feel free to get in touch with me. You've got my email address. So until next time, stay safe out there and feel free to get a hold of me if you need me. Thank you.